I'm delighted to be back at ATPESC. It's become an annual tradition of mine since the beginning, and I'm happy that I'm still adopted here. When I left to start KAUST in 2009, I was integrally involved in Department of Energy's SIDAC program, Scientific Discovery Through Advanced Computing, and part of my goal in taking up this opportunity, the world's third best endowed university on the shores of the Red Sea, was to reproduce SIDAC East, or SIDAC Middle East, and to complement the excellent activities that you've been hearing about, and we'll hear much more about today, with another source of funding and another demographic of participants. So how does this talk relate to ATPESC? Well, I'd say there are numerous tie-ins, because algorithms I like to think of as being in the middle, perched between the hostile architectures and the ambitious applications, and depending upon all the system software programming models and everything, forming the ecosystem that you're here to see in its full glory. So, of course, architectures today want more uniformity. For instance, if you're willing to do a 4x4 matrix multiply, get 64 flops in one instruction on the new Tensor Core from NVIDIA, which makes up the 3.3 exaops of the Summit system that I think you heard about earlier in the week. But that's a lot of uniformity. Meanwhile, applications want more irregularity, like the adaptive methods for memory efficiency that you'll hear about later from Mark Shepard and Sanyo Kolev. So there's an interesting tension in the algorithms community as we approach exascale. There are, of course, many other tie-ins to Jack and Jim, who you heard, and the Fast Math team and the SEED team coming today, to programming models, because we need to move away from bulk synchronous MPI everywhere to things that are much more efficient, potentially anyway, with local shared memory. And also I want to tie into Phil Collella's dinner talk, whose slides I downloaded from a few days ago, championing a resurrection really of the Mehrstellen technique from the 1950s or 60s, which is a great way of packing more accuracy into a stencil without packing in more data. So, you know, just using more points that are local, more operations on those points, get higher accuracy, store fewer points, get up the arithmetic intensity an order of magnitude from one Poisson solver like multigrid to another one like this fast Poisson solver that Phil is talking about. And as Phil ended his talk, changing the math can have a large lever arm. So that's a good way for me to begin. So I would like to introduce the two parallel universes of numerical linear algebra. The old flat brown one, where you're operating with a matrix, so you have a do-I, do-J loop, dense or sparse, but you assume that memory can be globally accessed at equal speed. And then there's the hierarchical universe, whether it's the scale-pack block ij, or whether it is the multi-level feature of multi-grid, or whether it's the domain decomposed feature of domain decomposition. We still have that matrix operation loop, whether it's a multiply or a factorization or backsolve, within a small piece of memory, but we have a hierarchy of those memory blocks that are designed for concurrency and for less synchrony. And the particular version of hierarchical linear algebra that I would like to talk about today, which I believe Sherry Lee will pick up on later this afternoon, is the H-matrix version. H-matrices are sort of a algebraic form of fast multipole. If you don't have a Green's function, you can still get similar compression, nearby elements interacting densely, large regions of far away being compressed, and this philosophy now has been algebraized. Now, this is about software this day. I'm not contributing directly to any of the DOE software that you'll hear about in the ECP, but in the ECRC at KAUST, we have our own software releases. These were 7 that were released at Supercomputing last year. HICMA, or the Hierarchical Computations on Many Core Architectures, is sort of our high-level API to solvers, eigensolvers, et cetera. The K-BLAS are a lower-level BLAS implementation on GPUs that use more recursive subdivision, more double buffering, and asynchronous scheduling than was the native cuBLAS, and now are in fact in the cuBLAS. The KSVD is a SVD and eigensolver that's based on Nick Hyam's QDWH, the QR diagonally weighted Haley iterations, which is a way of producing an arbitrary amount of concurrency in a polar decomposition, which can then inform a eigendecomposition or an SVD. The net effect here is doing a lot more flops than the conventional scale-pack methods. But you can, those flops give you more concurrency, the net result being that the computation can actually finish faster, and the asymptotic advantage grows as the matrices get larger. And this is now part of Cray's libsci. Gira is a sparse stencil evaluation package, which is motivated by the fact that on shared memory nodes, the most efficient way to do temporal and spatial blocking is not to give 1 over n of the cache to each of the n cores, but to have several of the cores sharing a bigger block of cache. And that leads to advantages up to a couple of x. And that is now, the student who developed that is now at Intel further developing it. The stars H is actually a hierarchical matrix library like the Florida sparse matrix package for standard sparse matrices. Exageostat is a maximum likelihood estimator based on H matrices, which can take statistics correlation matrices into the millions or billions. We've just provided an R interface for it. It's not part of R, but if you're an R person, you can access this package through the interface you're used to, and this is primarily motivated in our university by applications to geospatial statistics. The multi-objective adaptive optics, again, is a dense linear algebra package doing real-time alignment of tiny mirrors in the world's largest telescopes, and this is now part of the Japanese Subaru telescope in Hawaii and is scheduled for incorporation into the European Extremely Large Telescope, which will be the world's largest in a few years. So we are making software. You can download it at GitHub. I won't spend much time on the individual packages today. My role here is to give an overview of the algorithmic philosophy that your generation will have to confront in exascale and beyond. But I would like to point out that our center also employs 2 very active PETSI developers, Stefano Zampini and Lisandro Dalcin. If you use PETSI, you probably use their code. We're the largest PETSI developer group outside of Argonne, and we're very happy to be engaged on the sparse side as well as the primarily dense side that you see here. So my overall motto for you this morning comes from the hockey great Wayne Gretzky. A good player plays to where the puck is, while a great player skates to where the puck is going to be. So you're going to be great players, and you're going to need to be anticipating the kinds of algorithmic options that will balance better on future architectures. So you could say this talk is about algorithms for where architectures are going to be. So my outline is to just briefly, because you've probably had it in so many talks this week, remind you of the architectural constraints and some important new applications trends, in particular convergence of simulation and big data, which is motivating the investment in exascale. 4 algorithmic imperatives that come from those constraints. 4 sets of good news, bad news as we face this frontier. 4 sets of 4 widely applicable strategies in reshaping algorithms for exascale. And then if there's time, and my history shows that there may not be time, but they're in the slides at the back, I have some examples of ways that we are trading flops for data transmissions and so forth, and coming up with faster algorithms that would not have occurred to our forefathers or mothers when memory was flat, but now is the way to go in many ways. So you can count the 4s as we go through. First of all, architectural trends that you're familiar with. Clock rates have ceased to increase while we get more and more cores per node. Memory storage capacity does increase, but fails to keep up with this fast-growing arithmetic capability. Similarly, transmission capability, they increase, but they fail to keep up, leading to further and further imbalance. And the mean time between hardware interrupts on these increasingly complicated systems shorten, which suggests putting more of the resilience in the algorithms rather than keeping it all in the hardware or the operating system, because algorithms have a closer to the application's view of what kind of errors are important and how to react to them. In the meantime, billions of dollars, or your favorite currency, of open source scientific software, largely funded by the DOE and the NSF here, hang in the balance. We can build exascale machines, but we'll only get infra-petascale performance on them until we learn to use the new balance of resources better. The origins of this talk and much of my own interest in the last decade or so came from the International Exascale Software Roadmap project of, at that time, the G8 countries in the period 2008 to 2011. And you can download this roadmap. I'll summarize all I need to take from it in a couple of slides. That we need to get to about 50 gigaflops per watt of energy efficiency to reach exascale at affordable electric power consumption. Today we're typically at 5 gigaflops per watt. I'll show you a histogram of the top 250 machines and their power efficiencies in a few slides. You'll see that 5 gigaflops is approximately the knee in the curve. Processor clocks may be dynamically slowed or speeded. This might be schedulable by you, or it might be in the hands of the hardware. This makes the per node performance rate reliable, which means that synchronizing over billions of such cores will lead to lots of perhaps idle time, leading to the emphasis on asynchronous methods. The required reduction in power per flop and per byte moved may make computing and moving data less reliable. As engineers, that should be a trade-off that we're willing and eager to make to get more performance, provided that we know how to handle the resulting errors or potential inefficiencies. So here is that chart of power efficiencies from the June 2018 Top 500 list. 261 of the computers on the list reported their power efficiency, and you can see that there's 2 orders of magnitude difference from 18 gigaflops per watt to 0.18 gigaflops per watt in these systems on the top 500, with an approximate mean at about 5 gigaflops per watt. To get to exascale, this would require 200 megawatts, and that's unacceptable, so we have to continue to drive hardware up this extreme. I'm happy to say that the #1 system that was just released sits about there, so it's very power efficient if you can use those flops. This is a chart from Karen Bergman that she gave as a plenary at ISC about a month ago, showing over the last decade or so the relative, and notice this is a log scale on the left, the relative spread of imbalance between the node power in terms of gigaflops, and they're all set to 1 in 2010, and so this is the blue curve, and then the red curve is the bandwidth per node, and the ratio of those two, which is degrading, of course, as both the blue and the orange increase, is the bytes per flop ratio, which started out at a pretty meager 1/10 of a byte per flop. Think of, to get 1 flop on 2 double precision numbers, putting into a third, that's 24 bytes for 1 flop. And so to have 1/10 of a byte per flop is already very imbalanced unless everything's in registers. But it gets worse, because look how this has changed in the last 2 years. In the last year alone, the last 6 months, we had nearly an order of magnitude deterioration in this critical ratio of machine balance between bytes delivered to the processors. So we went from Taihu Lite at 0.004 to Summit at 0.0005. Summit has been used for some impressive things, but that's the algorithmic ingenuity of those who are using this incredible imbalance here. So it's not just bandwidth, of course, it's energy, as has been alluded to. These are also rough figures from Karen's ISC talk, showing 4 orders of magnitude advantage in energy for staying in cache, if you can fetch your next argument locally from cache or registers. And similar ratios, 10 to the 4th, exist for latency and as for bandwidth and energy. Power costs in perspective, that looked like small stuff, picojoules, right? But a pico of something done exa per second is a mega of something per second. And so 100 picojoules at 1 exaflops is 100 megawatts, and that's just for the flops. That's not counting moving the data. 1 megawatt year costs about $1 million, so this computer would be $100 million a year just to operate. But it also represents the electrical needs of 71,000 people and the carbon footprint thereof. So you can see why it's unacceptable to head to exascale by just replicating today's hardware, why we need to go to more severe power efficiencies. EXA is different from this factor of 1,000 every 10 years, this giddy ride that we've been on without having to change the programming model or the algorithms very much for the last few decades. Moore's law, it's controversial whether that's ending, but it's uncontroversial that Dennard's MOSFET scaling has ended. In 1972, Dennard published a paper showing that you could get kappa squared times more compute power for the same unit of electrical power if you increase the doping by a factor of kappa and reduce the line width by a factor of kappa in your semiconductors. So kappa squared times more flops per unit power, but unfortunately the copper goes the other way. When you shrink it, it dissipates more, and these curves have finally crossed, leading to the sort of stagnation in power per flop. So we've known for 4.5 decades that these trends existed, but only in your generation are they becoming serious obstacles. This is a chart that was in Phil Colella's talk. It's from the 2014 Proxy Architecture for Exascale report from Sandia. I have modified it to remind us that there may be even more heterogeneity coming than just the fat core, thin core model of today's supercomputers mixing CPUs and GPUs or mics. We may have even more heterogeneity on or near the chip as sort of single instruction, go off and do this operation quickly and come back and integrate it into my deterministic digital world. So this is another driver for algorithms. So there are architectural resources to balance. The processing cores, increasingly heterogeneous. The memory, increasingly hierarchical, partially reconfigurable on the fly. The intranode network, all the communication that takes place within a chip containing hundreds or thousands of cores, which in itself is non-uniform in terms of cache access and latency. And then the internode network. You've had several days on MPI, and you're better equipped to think about that than me right now as a result. But for performance tuning, you have to be identifying for each phase of your code which one of these resources is limiting, and then address your algorithmic adaptations towards that feature, and then you'll get the best possible, even if some of the other features are being exercised at low efficiency. The goal is to not get the most efficient for any one of these four, but to get the minimum runtime by adapting the algorithm. So there are well-established resource trade-offs. You heard Jim Demmel talk about communication avoiding algorithms. If you have extra memory per node, you can use it to reduce the communication volume and the number of messages. Very important work. You've heard from Bill Gropp, but probably not about his synchronization avoiding algorithms, also the work of Giesels at Berkeley, ways of rejiggering Krylov methods to do many fewer synchronizations at the price of doing more flops. Instead of taking each inner product when it comes, you can delay them, do a whole bunch of them in one global reduction, and then do some extra flops to make up for that. So it's an interesting trade-off. High-order discretizations in the spirit, for instance, of Paul Fisher here at Argonne, who has been promoting spectral element methods in PDEs for many years. If you can up the order, then you can get more flops per degree of freedom, which is good for performance, but most importantly, you can use less memory. So you're living higher on the memory hierarchy, you're accessing elements out of registers and cache instead of going down to DRAM in a sparse, low-order scheme. So exascale definitely focuses our attention towards higher order methods, and in fact, higher order halo-free methods like discontinuous Galerkin, because otherwise, if we have really big finite difference or finite element stencils, they may spoil our communication. So heading towards exascale, node-based weak scaling is routine. A sample exascale configuration is 1,000,000 1,000-way 1 gigahertz nodes, 10 to the 6th, 10 to the 3rd, 10 to the 9th, multiplied together. Expanding the number of nodes up to this amount or beyond would not be a serious threat to today's algorithms if we got the memory and the memory bandwidth to go with those extra processors. Just replicating cabinets, that's not bad. We have a log connectivity. Of course, this does require the nodes to be performance reliable, or we'll be held up at synchronization points. But the real challenge is not the weak scaling of cabinets, it's the strong scaling within a node heading towards thousands of cores, while the memory and memory bandwidth per node are not increasing at this rate. And of course, you don't need to wait for an exascale system if you're a PhD student at a university without many resources at the moment. You can start working on GPUs and mics and other many core devices coming along. So this is the familiar. We know how to scale this way. This is the challenge. We're getting very poor efficiency typically out of these inner processors. This is a diagram to remind you, symbolically of the complexity of the recently discontinued Intel Knights Landing processor, showing nested levels of coherency in the cache. So, a sort of a hierarchy of cache access based on different cores, and then a complete network within the chip, going off on the sides to MCDRAM and standard DRAM in different speeds and proportions, leading to a lot of different cache policies that are part of the algorithmic playbook now. Reminder, in 1997, this was the world's first terascale system, ASCII read at Sandia by Intel. It took nearly a megawatt. In 2007, this fits in something this size, a teraflops. We shrank a machine room to that size, but we also improved the power efficiency by nearly 4 orders of magnitude. And this trend must continue, even though it makes a more hostile ground for algorithms. Just looking at those two systems, they both gave a peak teraflops of about 1, about as featured many orders of magnitude different in power, and therefore the power efficiency, their ratio. Here are some other recent architectures to compare with that right-hand column: the Knights Landing, the Pascal, the Taihu Light, the Chinese self-fabbed system, and the new Summit, which reaches a power efficiency of 13.9 gigaflops per watt for the entire system. In some sense, these two are cheating because they're not reflecting the cost of memory and network in those totals. These are just chip totals. But this is a complete system coming in with the power efficiency of this chip. Very impressive, but still a factor away from the 50 that we need to get an exaflops at 20 megawatts. Okay. How are most scientific simulations, the ones you're doing, implemented at the petascale today? All the order n scale data structures are distributed. There's no duplicating the largest size data structure. Each individual processor works on a subdomain, owner computes, exchanges information, hopefully mostly with neighbors, sometimes globally synchronized, and hopefully the network scales so that the computation and the neighbor communication are fully parallelized and their ratio remains constant in weak scaling. The programming model we use is traditionally called bulk synchronous, or SPMD, or communicating sequential processes. We have 3 decades of stability writing to this particular architectural model. The name was given by Les Valiant, the Turing winner in Journal of the ACM in 1990, who noted that basically, just like the von Neumann architecture was a good intermediate that hardware people could target and software people could program to, and compilers and all that, similarly the bulk synchronous model, where you have a network that's used only in bursts, and you have a single node code that's the same for every node, just different data. That's a convenient programming model, and the architectures can target it too. But notice that it's very inefficient in one way. The network is sitting there idle a lot of the time. When you're bulk synchronous, you're overusing a resource in bursts, if you could spread things out, you could get a better balance. So here's a typical domain decomposition for a PDE, where the local work concentrates within a node, and there's let's say in this case, n squared work within a node and order n across it. In 2D, n cubed and n squared. In 3D, a balance that can remain in the favor of the computation to communication ratio as we weak scale. And this has led to dramatic improvements in delivered science. The Gordon Bell Prize is perhaps more interesting to track than the top 500 list, because these are gigaflops delivered to real apps like reservoir models, materials science, mechanics, celestial dynamics, and so forth. And starting from the year that Gordon Bell was created in 1988 until the next couple of decades, there was a reliable factor of 1,000 every 10 years, and at the same time, as reflected in Gordon Bell Price Performance Prizes, which are unfortunately rather sparse. But we can track these 3 decades and see that nearly a factor of 1,000 in price performance has occurred simultaneously with the absolute performance if cost were no object. So we've been riding these exponentials from giga to tera to peta with the same model, same assumptions about who cares about what, who cares about errors, who cares about the communication, who cares about the node code. Same classes of algorithms, but now we're at a crossroads because of the architecture. And EXA appears qualitatively different, not just quantitatively, and looks more difficult. But don't forget, we once said that about message passing. Message passing was resisted by many applications people in my generation. Now it's embraced as a way to control the most difficult part of your code to engineer for performance, namely the communication. And we'll have similar embrace of the difficulties of exascale just to maintain relevance, let alone for the intellectual stimulation. Almost all good algorithms today in linear algebra, differential equations, integral equations, and so forth like to synchronize. We do inner products, we do norms, we do pivots, we take fresh residuals to evaluate progress. This already tends to hurt efficiency beyond 100,000 processing units. It can even be fragile for smaller ones due to adaptivity and hardware performance variation. Even if, for example, there was a famous example by Phil Colella where the look-ahead buffer was different for one node of a cray than for all the other ones, and it was very hard to find that synchronization bug. So concurrency is heading to the billions of cores. And so the bulk synchronous generation must pass the baton to your energy-aware generation. And that's what today is about for algorithms, and what these few weeks are about for the whole ecosystem. And the latest report in the series that began with the International Exascale Software Project, the IESP, is the BDEC. Both of these reports are found at exascale.org. Both of them are sponsored by, in this case, the G7 countries for BDEC. And this new report has just come out emphasizing a inflection point in applications much like the inflection point in algorithms and hitting at the same time, namely the need to converge big data and extreme simulation. Today, these worlds are largely separate. You know that if you're in the big data world and here sort of feeling maybe a bit out of place. Your software has names on the left-hand side here that many of us on this side don't even recognize. Hive, Pig, Scoop, Flume, of course, MapReduce, we all know. But notice that the only elements of this software ecosystem that are shared are the operating system and, I guess, MPI. Other than that, these are separate software ecosystems. And the hardware is used in different ways, batched versus interactive. Temporary large storage versus multi-decadal archival storage, different modalities of operation altogether. But by coming together, we can gain many benefits. And this is a table from this report showing the off-diagonal benefits of combining the third and fourth paradigms. And the fourth paradigm is divided here into analytics, which is sort of standard MapReduce, where the algorithm doesn't change with the data, and learning, where as the algorithm ingests data, it actually becomes smarter. And these are also two almost separate worlds. But if we could integrate in an in situ way the analytics and machine learning into the simulation world, we could do more efficient steering in high-dimensional parameter space, pruning the number of simulations to be done, and in situ processing of the results rather than writing gigabyte or terabyte or petabyte files to disk and reading them back again in a separate execution. And learning could provide smart data compression and even improvement of the simulation. For instance, think of climate modeling with the empirical functions for cloud albedo and viscosity of gyres and so forth. You could even learn those functions better. They're not first principles in many cases. Simulation, on the other hand, provides many benefits to big data, including for analytics, which is essentially sometimes having to choose between equally probable events without any guidance on which one satisfies the conservation laws. So we speak of physics-based regularization coming from simulation. And to learning, a lot of big data isn't really that big. For example, think of the machine learning that's going into training the ITER reactor when to shut down if an instability is developing. The ITER reactor's heading towards about $25 billion. You don't want it to break very many times to track the real transients. You want to break it on the computer many times and learn which transients are heading towards one of those plasma instabilities and build up that database for real-time monitoring of an expensive experimental apparatus. And the third and the two fourth paradigm families also have various benefits to each other. Now, what's the implication here? The implication is that we're taking two highly complex software ecosystems, big data and extreme computing, and trying to merge them in situ in one executable inheriting all their error modes and the new error modes that come from their unpredictable interactions, living on more hostile architecture, but all for much better, much more efficient, ultimately, science and engineering, and the stakeholders for exascale expect this. So the four algorithmic imperatives would be obvious coming from this part so far. Reduce synchrony, either in frequency of global, or in span. You don't mind maybe lots of local synchronizations like within a node. Reside high on the memory hierarchy, that is to say have smaller working sets accessed more frequently. Increase the single instruction multiple thread or single instruction multiple data style shared memory concurrency. So for example, you can get 64 flops in one instruction from a tensor core if you can program to that very special operation. Build in resilience in the algorithmic space where possible. The bad news, we must explicitly control more of the data motion because it carries the highest cost in both time and energy. The good news is we'll have more opportunities to control it, more language features to say where data should live, how frequently it should be refreshed, whether it can be written back bypassing intermediate levels of cache, all these kind of things that can lead to huge performance gains. They're not really under our control in many ways now, but they will be, just like horizontal data motion is through MPI. The use of uniform high precision in nodal bases and dense grids may decrease. We are lazy. You know, we have double precision, we have big memories, we store a nodal value at each point. These are continuous functions. They're continuous in space and time. Why store nodal values? We should have some hierarchical representation, much the same information in many fewer bits, and therefore moved around faster. And also, why store full values? If you think of 10,000 MPI exchanges between neighboring processors and you monitor the data, chances are it's only changing from iteration to iteration in the least significant bits, but we, of course, don't recognize that. We send everything. And this was, of course, acceptable when memory was flat and communication was cheaper than computation, but that's no longer the case. So as engineers, we have to go in and look for what to optimize. We need to equidistribute errors. We may be willing to tolerate lossy compression in compressing a message, sending it, and uncompressing it in order to get better efficiency. And of course, the stability implications of that have to be studied. Fully deterministic algorithms may be regarded as to synchronization vulnerable. If we're waiting for missing data, we might try to predict it. Apply machine learning to the machine and go on. And if it turns out that was mispredicted, we can always roll back. But chances are, in a continuous problem with good machine learning, we can actually adopt more and more of these exciting models. And that will be a rich mixture of numerical analysis and statistics. Fully hardware reliable executions may be regarded as too costly. So I've harped a little bit on algorithmic-based fault tolerance. It's been around in linear algebra for a long time. It's getting incorporated more and more into other sections of the software stack. Back in 1956, von Neumann did not have reliable processors, and he wrote a paper about the synthesis of reliable organisms from unreliable components. He was talking about cellular automata, but the same kind of philosophy has to be turned now to our floating point work. So I come back to the ambitious applications in the austere architectures and you know, we algorithms people, most of whom you'll be hearing from today, are in that middle. But it's a full employment program, so welcome. So what will exascale algorithms look like? Well, they have to be optimal to start with because flops are a proxy for data motion, at least at the big end scale. We can have polynomials in K, where K is the rank of a block, or K is the degree of a high order element, but we have to be order n or order n log n in the total degrees of freedom. And every decade for the last 50 or 60 years has introduced an algorithm of this nature that replaced a polynomial algorithm. And the one that many of us are excited about is H matrices, which is sort of a generalization of fast multipole to variable coefficients. And of course, randomized algorithms are another very exciting thing. The Gunnar Martinson school of like doing an SVD with order K matvex rather than order, so it's order Kn KAUST instead of n cubed to do a full SVD. And as one of my PhD students wrote in his thesis, with great computational power comes great algorithmic responsibility. So this is the software stack that we need to migrate to the exascale. Most of you probably work in this left-hand column. Today you'll hear about meshing, discretization, solvers, adaptivity, certain things in that column. But it's also important to get the development-related software, the compilers, the debuggers into the exascale, the profilers, and then, of course, the production-related workflow management and managing the data files and so forth. So high-end computers come with very little of this. Most of it emerges initially in PhD theses and postdocs and then gets hardened by the groups whose representatives you're going to hear from today in fast math and seed and so forth. So this is actually past the midpoint in time, but it's sort of the midpoint it's a chance to pause before we go into a few weeds maybe. We want new formulations with reduced synchronization and communication, less frequent and or less global. Reside high on the memory hierarchy because we get a benefit of faster access and can use the less memory per node that we're going to be given. Greater focus on ways of producing uniformity. For instance, a warp can do 32 of one thing if we can break the original computation into 32 of those things to do at the same time. And then algorithmic resilience. We have to quantify trades between limited resources so we can tune the algorithms. And then finally, we can go on to all the post-forward problems. I've been speaking in terms of maybe Schrodinger's equation or PDEs or gravitation. Those are the forward problems. But we want to move to the post-forward problems of optimization, data assimilation, parameter inversion, the mixtures of the third and fourth paradigms that require loops around the forward model, and therefore that forward model has to be very efficient. So, strategies to address these. The first one is to, wherever possible, move away from the bulk synchronous model. It's convenient to program and to debug in, but we need to go to less synchronous models based on directed acyclic graphs, and there are many instances. Some of these, of course, like OpenMP, has had for a few years a task-based feature. Some of the other ones are more experimental, and you'll be hearing from a few of these during the week, I noticed. Pay attention because these are important ways to restructure synchronization at the small scale. We need to exploit data sparsity where it exists. If we want to get to covariance matrices of millions, we can't store 1,000,000 times 1,000,000 trillion double precision floats. We have to shrink that using the sparsity that's naturally in the data based on decay with distance in many problems, both physical and statistical. So we need to meet the curse of dimensionality with the blessing of low rank. It's always been there, but we didn't need to address it until now. We need to employ more high-order discretizations because of their memory and communication efficiency, and of course, because most users of these systems won't want to go into these level of weeds, we need to code to a high-level API, like solve my eigenproblem, or solve my Poisson problem, and have many targets of the architecture underneath. So of these four strategies, a couple of slides on each. Taskification based on DAGs. Maybe Jack talked a little bit about this, but we need to remove, our libraries today are full of artifactual synchronizations For example, subroutine boundaries, or loops that are prescribed in the order in which the indices are varied. We need to expose more concurrency where it exists. Of course, we have to pay the overhead of managing a task graph and declaring those dependencies in a small scale. And if we load balance by moving data around to the less busy cores, we may potentially lose some memory locality. So these are the things to trade off against the advantage of less synchronization. Here's an example for a classic generalized eigensolver, for instance, Schrodinger's equation, where we would first factorize the B matrix and apply its factors to the left to get a regular eigenproblem, then do a tridiagonal reduction and a QR iteration. And the first three of those steps are compute intensive, and on a little 4x4 matrix, rather than 4 million by 4 million, I can draw the task graph. And this is time down, and this is the successive subroutine calls. How much better is this? This is actually a more tightly packed in time, more concurrent in space execution pattern for exactly the same eigensolver. This can even go to the point of scheduling many loops at the same time. For instance, in our adaptive optics application, if you zoom in on that particular group, you'll see that tasks from 3 different loops of this dense matrix manipulation called the optical reconstructor are actually executing simultaneously. The second thing is to go low rank where possible, to replace dense matrices or all-to-all coupling like the inverse of diffusion operators or gravitational attractions or whatever, electrostatics. Replace those with data sparse representations. We want to shrink the memory footprints to live higher, reduce operation counts, and we can tune the work. We can have, in the limit, we can go back to a dense coupling, losing no accuracy. In another limit, we can lose a lot of accuracy and have an extremely sparse representation that may be useful as a preconditioner. Of course, we have to pay cost of compression unless these operators can be born sparse, and there is a lot of progress using randomized algorithms to create the sparse representations directly from effective matvex or function evaluations without first building the dense matrix and then compressing it. But whatever the case is, order matters, the order of unknowns, and not all operators compress well. Random matrices don't compress at all, for example, but Poisson matrices compress beautifully. This goes back to Hackbusch's work about 20 years ago, noting that the off-diagonal blocks of typical differential and integral operators have low effective rank. And by exploiting that feature, you can get algorithms that are ln-log in n, polynomial in k, with constants that depend on the accuracy retained. There are many ways of structuring the interactions between these blocks. You can have fewer blocks of larger rank, which is called weak admissibility, or more blocks of smaller rank, which are more complex to describe in the hierarchical data structure. But before I show you those, let me remind you that you already know this. There's the 1D Laplacian. You know that the off-diagonal blocks are low rank because you can see that they're almost all zeros, right? But the inverse also has off-diagonal blocks of low rank. This is a rank 1 block. It has n squared numbers, but it can be represented by 2n vectors. And this is an exact representation for a constant coefficient problem. For a variable coefficient problem, I may need to store a few more vectors in that cross product. We can build up these matrices hierarchically by saying, is the rank small enough in this full block? If no, subdivide. Is the rank small enough? If no, subdivide. Now these off-diagonal blocks can be represented with low rank. Subdivide the blue ones again. Save the red ones. Don't try to compress them. They have high rank, but you can recursively build up these structures. This is the strong admissibility case where almost all these blocks have the same rank. And this is the weak admissibility case, a simpler data structure to think about implementing, but these off-diagonal blocks may cost you in the K order. High-order discretizations. I already alluded to some of this along the way, but these are their virtues. And the disadvantages, of course, is that some of our optimal algorithms we have less experience on the high-order things. Some things like algebraic multigrid and H matrices don't work as well on the high order as they do on the low order, at least not yet. But there are some encouraging results for HPFMM on terms of compression coming. An example executed with some Argonne collaborators, actually, and Chicago collaborators a few years ago for a Gordon Bell attempt, is to do a CFD code a simplification of Paul Fisher's NEC 5000. And you'll see on this chart, which I won't go into in great detail, that we took the element size from 4th order to 32nd order, which sounds ridiculous, but it actually gave the best performance, not 32nd order accuracy, but the best choreography of data in and out of the course. So on the left is the gigaflop scale, and that's the histograms for 4 different programming models: Intel MKL, Paul's own convolution operator, Intel's libx SMM, and libxMM with non-temporal stores to improve the cache performance. And you can see that within each order, generally the purple one is the winner, and there's an increase towards asymptotic. You're getting almost BLAS 3-like efficiency at the upper end. In the meantime, the curves show the gigabytes per second for the 4 different programming models. Same accuracy, but less runtime. So here's a measure of the accuracy. Here's a cost in total number of core hours. So by going from 14th to 28th order, for example, from 16 small elements to 4 bigger elements, for the same accuracy, you're getting a few powers of 2 less cost. The last of these 4 recommended practices, of course, is the necessary one of coding to the architecture by idioms like tiling, recursive subdivision, targeting batching, reducing call overheads, but being polyalgorithmic based on the block size, and being clever with how memory is handled. Of course, the code is much more complex, harder to debug, harder to archive and adapt to new architectures. It's very architecture specific at the bottom, but hopefully, at the top, people can have a constant thing to target. So where do the cycles go if we're going to undertake this campaign? There are really 2 classes of compute-intensive inner loops in the DOE portfolio, many more than 2, but these are 2 of the biggest ones on the simulation side. Linear algebra on dense, symmetric, or Hermitian matrices. That includes chemistry, that includes optimization, that includes mechanics, that includes statistics of very large problems. Poisson solves, PDEs in fluids, solids, E&M, density functional theory, molecular dynamics, gravitation, electrostatics, and so forth. These are the big Amdahl blocks to attack. And if you're a student in my group, you have to tell me which of these 4 algorithmic things you're working on. which of these pucks, where are you? What puck are you skating towards? So some examples, and I'm going to run out of time in about 7 minutes, and I'll just maybe get into 1 or 2 of these examples by way of illustrating the trade-offs that are possible. I already alluded to this QR, diagonally weighted Haley decomposition form of doing dense eigensolvers and SVDs and the K-BLAS. There's an algorithm that's now part of PETSI called balancing domain decomposition with constraints. This is a linear preconditioner that does local Choleskis and local eigensolves on interface. It's very flop intensive, but that flop intensivity is only related to the degrees of freedom per subdomain, not to the size of the problem. So you can weak scale out to big problems. Guarantee low condition numbers. What does that mean? That means few Krylov iterations. That means few global synchronizations for a predictable amount of work per load. It's a good trade-off, and it leverages all the work that you do, in the Cholesky solves, which can of course be replaced with low-rank Cholesky solves, since these are often diffusion-based operators. Fast multipole, not a new algorithm. I think it's actually 32 years old now. This slide wasn't updated. But of course, it's normally used in so-called full precision, but it doesn't usually beat multigrid in full precision. Fast multipole is asymptotically faster, but slower in practice on many codes because of big constants. But if you roll back the accuracy, lower the degree of the expansion of the multipole, then it can be a competitive preconditioner. This is accelerated cyclic reduction. Cyclic reduction is a 53-year-old algorithm going back to Gene Golub, actually, and people at Los Alamos. They noted that if you had a constant coefficient Poisson solver, you could use FFTs to successively reduce the block size and get an order n log squared n method. by recursive Schur complementation and diagonalization. However, if you have variable coefficients, the FFT won't diagonalize, but it's still a highly compressible operator, so H matrices can do that. A lot of our problems are nonlinear. And in nonlinear problems, we have global synchronizations coming from Newton's method, and we have large, sparse linear systems to solve that are often ill-conditioned at every Newton step. This produces lots of global synchronization at the Newton level and at the Krylov iteration level. If you precondition nonlinearly, that is, break your original nonlinear problem into a bunch of smaller nonlinear problems, the union of which has the same root as the original, then this helps with the synchronization. And this is a family of algorithms called asynchronous, additive Schwartz precondition inexact Newton, which is now part of PETSI, and maybe Barry will talk a little bit about that this afternoon. And then I referred to Neckbox, this high-order CFD solver, to minimize runtime for a given accuracy. We don't care about the asymptotic accuracy of the discretization. We want the minimum runtime and the minimum energy for a given accuracy. So very little time to illustrate, maybe just the first one. This is the QDWH SVD solver. You can factor any matrix into a unitary thing and a positive definite thing. The positive definite thing can then be standard, go through a standard SVD, and the overall A matrix can be then represented by as an SVD with the multiplication of these two factors. By the way, this polar decomposition is so named because it's like, Z equals e to the I r. This is like the r, and this is like the e to the I in the complex plane, generalized to many variables. This iteration, which was called back to the community's attention a few years ago by Nick Hyam, the current SIAM president, is beautiful for exascale because it's recursive divide and conquer, it's backward stable. You can break a problem of millions down into problems of any size you want that fit a warp, and then go back up the tree. And of course, the inside is based on vendor-optimized kernels, Cholesky QR and BLAS3 gem. The complexity is very bad. It actually depends on the conditioning. It's an iterative method. But compared to the few n cubed of a standard SVD, this looks horrible. But it actually can be made to finish faster because it can fill up especially a many-core chip much more efficiently. So there are 3 ill-conditioned problems in solid, and 3 well-conditioned problems in dash. And if you look at the comparison of the Scala-Pack standard algorithm and the QDWH with Scala-Pack interior, you can see nice speed-ups. This is for a distributed memory computation of a couple, 100,000 by 100,000 matrix. Here's a single 32, these are both distributed computations, I guess. That's KNL. This one is Haswell, similar benefits. And as I mentioned, now part of Craze LibSci and being now integrated with a new accelerator that comes back from the 1880s by Zolotarev with Nakatsukasa at Oxford. So algorithmic reinventions come back. This is the original synchronized version of the algorithm. This is the taskified version. Time is to the right. So all this dead space has been squeezed out by the DAG, and this is taskified on a hybrid architecture of 32 Haswells and 8 NVIDIAs, and I guess I'll just sort of I have about a minute left, so enjoy the slides if you care for them. But let me just go to some conclusions. So this is one conclusion. This is the way the internet works. You have something called TCP/IP that handles a huge range of applications, from scheduling your trains to shopping on a huge range of architectures, but somehow this magic interface handles all. Not very well anymore, especially with security, but this is the algorithmic philosophy that today's leaders of the ECP projects are targeting. So how will we adapt? Let me just go to this concluding slide with 20 seconds left. Plenty of ideas exist to adapt or substitute for your favorite solvers that satisfy these 4 directions of algorithmic innovation. The programming models and the runtimes may have to be changed to accommodate. But everything should be on the table for trades, and this is this co-design keyword that you'll be hearing all week. And with that, I thank you for your attention.
Are there any questions here?
So building for resilience, wouldn't that affect performance?
Yeah, resilience is something I'm not personally addressing very much. Jack, of course, has a lot going on in that regard. One of my favorite examples of an algorithm that has built-in resilience that you don't often think of, for example, is multigrid. You suppose that you have a floating point error that gives you a delta function in your residual. If it's a diffusive problem, that's going to die away very quickly. So rather than make the hardware do sort of a triple replication or whatever, let the math say, aha, based on the quantities of interest, I know that I can ignore that one. And there's a lot of such things that we can build into today's methods. If we know the goal rather than being concerned about the exact bits.